Good morning everyone. Today we'll continue our discussion on op-amps and look further into circuit design. The learning outcomes of today is understanding the principles of filtering, and we'll be looking at circuits to implement this, and we'll also look into additional circuits and then try and design our own circuit as a sensor subsystem. So our aim is to build our own distance measuring sensor, so similar to what we discussed in the robotics last week. So we'll look to try and design our own. In order to do this, we'll have to firstly discuss filtering, and then we'll look at some other circuits that you will find both useful in this module and potentially in project work. And then we'll put all these ideas together to build our circuit. So the first topic today and the first video is on passive filters. So imagine we have a signal. So this is our signal here. So it's an AC signal, but it's got a DC bias to it. And we wish to amplify this. So if I just sketch this here. If this is our maximum level we can achieve, and our signal, AC signal, is up here somewhere, and we try to amplify this, what will happen is we'll amplify it, but then it'll get clipped at this maximum value. So we're not gaining much amplification before we're limiting the signal. So ideally what we'd like to do is get rid of this DC bias and move our signal down to be around this level. So when we amplify it, we can amplify it the full range. So filtering lets us get rid of large background DC signals, and it also helps us get rid of noise. So a lot of electrical noise is at high frequencies, so potentially we can remove all this high frequency noise as well with filters. For a filter, then there's various criteria we'd like, and in the ideal filter, so down here, we'd like zero attenuation at the frequencies that we are interested in. So any frequencies we want to pass through our circuit, they don't get affected at all. All the other frequencies are infinite attenuation, so what we are saying is they get completely removed. And the difference between these frequencies, the ones we want and the ones we don't want, this is a step transition. So we either definitely keep them all or definitely remove them. And there's no in between. So as an example of a filter, this might be our original signal. So you can see it's quite noisy. So what we've got, first of all, we've got a DC offset. And in terms of frequency components, it is this here. We've got our signal of interest, which is this gentle undulation. And that is our signal at this point. And then you can see we've got some sharp spikes, which is our high frequency noise. And this is this frequency up here. So we'd like to remove this, and keep this part. So if we put a filter on there, that only allows this part through, then when we pass this through this filter, what we come out with is a nice clean signal here of the frequency of interest. There's various types of filters. So in this case here, this was known as a band pass filter because there's only a certain band of frequencies it's allowing through. So this is our band pass filter here. We could just allow low frequencies through, and this is our low pass filter. Alternatively, just allow high frequencies through, and this is our high pass filter. Or we could let all frequencies through except just a few that we do not want, and this is known as our notch filter. This is essentially the inverse of our bandpass. So our bandpass lets a few frequencies through, the notch blocks a few. So we said we'd like a step change. So we've said here, this part, we want a step transition between accept and reject. In practice, there's a roll-off between these bands. So if we look at these filters here, ideally for a low pass filter, we'd have a line along there, straight down and along as a low pass filter. In reality, this is more of a gentle curve at this point. So we're getting roll off on these filters, and what we can do is quantify that. And if we say we quote the attenuation of a filter, so the amount of signal that goes through in dB, decibels, and decibels equals 20 log to the base 10 of the voltage out compared to the voltage in. So we can quote our filters here. So if I just exit that and restart, we can quote in our filters a point on the roll-off, which we'll quote just here. And this distance here corresponds to a drop of 3 decibels. So if we are saying the attenuation is 3 decibels, so it's minus 3, then if we work this through, we find out that the output is going to be about 70% of the input value. So when we look at filters and quote their specifications, we quote this minus 3 dB point as the frequency at which the output is 70% of the input value. We've been talking about attenuation, or the size of the signal, and we should also make a note that the filter introduces a phase shift as well. So the phase of the signal will also change going through a filter. Filters can be split into 2 basic groups. We've got passive filters, and passive filters are combinations of resistors, capacitors and inductors. They are simple to design, but they can be affected by circuitry next to them. So to give you an example of that, if we just go into Paint, so if I draw this filter, so this is known as a high pass filter, so it'll pass high frequencies. We'll call this C, and we'll call this resistor R1. So this filter has got certain properties which depend on its capacitance and its resistance. If we add something else after this filter, so say another resistor R2, then now we've got a combined resistance there defined as 1 over R is 1 over R1 plus 1 over R2. And therefore this filter will change its characteristics because its resistance has changed around here. Okay, so when you use passive filters, you have to be careful of the circuits you connect it to. I will just make a point in passing at this point that if we had this circuit, if we take back to our original filter, we've got C and we've got R1 in there. If we put this circuit in here, which is our op-amp, so we have got an op-amp in now, and then we put a resistor R2 in there, so we've got a capacitance here and a resistor. The combined resistance of this 1 over R equals 1 over R1 plus R2, where this resistance of this combination, we've got R2, and we set this had effectively infinite input impedance. So this is infinity plus R2. So this term is 0, and therefore R is still R1. So by putting this op amp in here, then we have managed to preserve the characteristics of our filter here. And if you remember from yesterday, this circuit here is our voltage follower. So it's a non-inverting amplifier arrangement with unity gain, and it was to isolate different parts of a circuit. So in this first case, our additional resistor has affected our circuit. However, because we've used this voltage follower to isolate circuits, then by adding a resistor, we haven't affected our filter. So that's one application of where voltage follower might come in. So they are passive filters. In terms of active filters use op amps. So there's a little bit more involved in designing them, but the surrounding circuitry has little effect. So in that respect, they're a lot more robust. The simplest filter design is a passive low-pass filter, where we've got a resistor here and a capacitor to ground here. The passive high-pass filter is virtually identical, except the capacitor and the resistor are interchanged. So for the high pass, the capacitor is here and the resistor is here. So for this passive low pass filter, we'll have a look at the transfer function. If you look at the current passing through the resistor and capacitor, we have the potential difference. So this is V in here, this is ground here, so we've got a potential drop of V in across here. So the current V equals IR, so the current is the potential drop over the impedance. So the impedance is the resistance plus the impedance of the capacitor. And if you remember from yesterday, the impedance of a capacitor is given by 1 over j omega c. The output voltage, so V out, so the potential difference between this point and ground here is just V out equals the current times by the impedance through the capacitor. So V out equals I times the capacitor impedance, and we know I is from this equation here, so we substitute that in, we get this term, and then if we substitute in ZC and rearrange, we get our transfer function out, which is this term here. What we can do is rearrange this. So we've got a complex number here, we've got j here. So if we multiply this by the complex conjugate, j omega c r, and then if we multiply it by 1 minus j omega c r over 1 minus j omega c r, so multiplying it by 1, we will get a real term, so we'll get a and an imaginary term, bj. And if we work out the amplitude and phase of that, the amplitude is given by a squared plus b squared square rooted, and the phase is given by tan to the minus 1 of b over a. So we can put that amplitude term in there, the phase term in there, and then we've replaced our transfer function, or we've reformed it to now be described by an amplitude and a phase term. So I'll leave you to do that as an exercise, practicing some of your mathematics. So this is our transfer function, V out over V in is this term. If we plot that out, what we find is at very low frequencies, this is your output here. So it's got a large magnitude compared to V in. So it's the largest magnitude at these low frequencies, and it's along the real axis, so it's in phase. As the frequency increases, you start moving along this line, so the output is here. So at higher frequencies, the output is moving this way, so it's getting lower in magnitude, and it's also now getting a phase change on the output. And then at very high frequencies, it'll go to very small magnitude with a 90-degree phase shift here. So what we can do is we can plot this out in terms of frequency. So we can plot frequency here against magnitude, alternatively against phase. And this is known as a board diagram. So we could work this out. The easiest way to do it is to represent it in Laplace form. So that's it in Laplace form. So if we remember back to here, we're representing it just as Laplace. So represent it as Laplace, we're putting some values, so say a resistor of 1 kilo ohm and a capacitor of 1 microfarad. We can just use some MATLAB code to quickly plot this up. And you can see this is a low pass filter, so it lets through low frequencies, and then as you get to higher frequencies, the signal gets attenuated. And we're getting a phase shift on this signal. So at low frequencies, there's no phase shift. As the frequency increases, the phase shift is increasing to a point where it gets to a 90-degree or minus 90-degree phase shift. We need to somehow define this filter. And the way we define it is we specify the 3 dB cutoff point. So it's when the magnitude has dropped to 70% of its original value. So if we put in, so we have omega here, or omega squared. So omega equals 2 pi f. So we put in 2 pi f squared in there. We put in our minus 3 dB, which is 70%. We rearrange this equation and we find the frequency when the attenuation is 3 dBs is given by this equation, 1 over 2 pi RC. So in terms of our plot, it is somewhere around 3 dB point. So appropriate RC values will give us our frequency, what we want to design for. If you notice at the 3 dB point, the phase change is 45 degrees. Now that was a passive low pass filter, which is essentially this here. So this is the first of potentially many passive filters we could design. So this is just a quick introduction into it. We'll be moving on to active filters, but that was just to sort of highlight how to design a passive filter. But as you can see, so this is a page from Wikipedia, and there's lots of different arrangements we can use for passive filters. So the more components you have, the better the performing you will be. So if you're into sort of filter design and want to do more elaborate passive filters, then I recommend you having a look at this as a starting point. So that was passive filters. The next video will be on active filters, and that's when we're using op amps to design the filters.